So whoops, sorry about that. Memory ran out on the phone, had to unload some stuff. So here we are. I have two objects on my uniform board. So let's draw in the forces. Now, we're going to draw in the forces that are acting on the beam here. So the first thing we're going to draw in here is the force of gravity on the beam, or the board, I guess I'm calling it here. Right, and notice that's coming from the center of mass of the object. We're also going to draw in the normal force of the pivot on the board, which happens to be at the center of mass. It doesn't have to be, as I've demonstrated before. Now, next, technically what we should be drawing here is a normal force of this object, which was, I believe, the lime on the board, and the normal force of the canister on the board. But we know that the normal force of the lime on the board is going to be equivalent to the weight of the lime, and the same thing with the canister. So this unit and this unit only, we're going to skip that sort of intermediary step, and we're just going to draw in FGL and FGC as if it acts directly on the board, which is not technically correct, but we're going to save ourselves a little bit of time and effort in this unit. Now, I'm going to draw in two other things here. I'm going to draw this and this. And so this would be lever arm distance for the canister, and this would be lever arm distance for the lime. Right, so you'll notice on my free body diagram now, I have all the forces acting, and then near the free body diagram, I have drawn in all of the relevant distances. This is going to be our new number one step here for these problems, is a free body diagram, and near the free body diagram, but not on the free body diagram, draw in all the relevant distances. It's going to make our lives a lot easier when we come back to construct equations. So, step one, free body diagram. Step two, as always, axes and declarations. And so here I'll make up positive and I'll make clockwise positive, right? So technically clockwise, if we use my right hand rule, is into the page, right? Curl your fingers in the direction, thumb points in the direction of the vector. But being that we're only going to have torques that cause clockwise or counterclockwise rotations here, we're just going to shorthand that and just say clockwise is positive there. The last thing that we need to do in declarations we've already done. We've put in the pivot point, right? So that's the most important thing that we can do for these problems, is put in that pivot point. So what are we doing here? Well, it would kind of depend upon what information I'm given. Let's say the mass of the board is 1 kilogram. The mass of a lime is 0.5 kilograms. We don't know the mass of the canister because it's filled up with an unknown amount of water. Let's say that we know this is half of that distance there, so it's 15 centimeters. Let's say that L, capital L here, is 30 centimeters. So the line was at the very end. And we just don't know where the canister was. And maybe that's our question, is where's the canister? So here we go. So the first thing we're going to do here is we would always try and think if a sum of forces equation is going to help us. Now in this case it's not going to, but I'm still going to demonstrate. So sum of forces in the y direction is equal to MAY, and we know that this is going to cancel out to 0 because that's the whole thing for this entire unit. So I've got a plus Fn minus FGL, subscript L, minus FGB minus FGC is equal to 0. Okay, well, I know the mass of FGL. I know the mass that goes with FGL and C. So it's really just, or excuse me, with B. So I don't know this, and therefore I don't know this. So if I needed to know the normal force, I would first need to find out what the mass of the canister is. So Fn is just going to be equal to the mass of the lime times G plus the mass of the board times G plus the mass of the canister times G. And I'm going to leave a little space under that in case I ever cared about that. So here we go. Sum of torques about the pivot is equal to I alpha. We know that that's going to go to 0. And so I ask myself, well, what forces cause torque? Right? Remember, a force causes a torque if the line of action of that force does not go through the pivot. So therefore, because the pivot's here, FGB and Fn are not going to cause a torque. So let's ask what causes positive torques. That's clearly FGC. That would cause this thing to spin clockwise if there was nothing else acting. So I'm going to do plus torque due to C. Next, there's no other positive torque, so we're just going to put in minus a torque due to L, and that's going to equal 0. And so my next line here, what I'm going to do is plus parentheses, 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 minus parentheses, 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 parentheses equals 0. Now, it's a very short expression, so I didn't need a lot of space for it. So what are the two parentheses? Remember, force times lever arm. Here, because all my forces are vertical, all my lever arm distances are horizontal. So here we go. So this would be FGC, lever arm for C, FGL, lever arm for L. Okay, and this is almost trivial now to solve because I can plug in what I need. Mass of C times G, L for C, is that what, oh no, I actually need to either know L for C or know M for C. I didn't give you enough knowns in order to solve this problem. Let's say that this is, it was closer and let's say it's 5 centimeters, and then we can solve. So L for C is, we'll put in 5 centimeters minus ML, right, G, and then this we know is 15 centimeters is equal to 0. Notice, I know a lot of things are canceling out here, so I'm not too concerned with my units. I can see that my G is going to cancel out, so I don't really care about that. I know that the mass of the lime is 0.5 kilogram, which is totally ridiculous. Limes are not that heavy, but let's just run with it here. 0.5 kilograms, and then this is 15 centimeters over 5 centimeters, which gave us that this mass was a lot larger, 1.5 kilograms, which should make sense, right? If you've ever been on a seesaw, right, if you have 2 kids of equal weight here, they can balance. But if you have one kid who's heavier than others, say for example me when I was a kid, I was told a lot, the fat kid sits closer, so come on, scooch up, fatty, and there you are. So that was me, unfortunately, the canister. The heavier kid sitting closer into the center. It was a sad fact of my existence. The playground was a very cruel place, but now we have the math to prove it.